In this video, we'll begin to look at graphing polar equations. So the graph of a polar equation r equals f of theta, which would be similar to thinking y equals f of x, so r equals f of theta, consists of all points p that have at least one polar representation r theta, which would satisfy the equation. So many curves that arise in mathematics and applications, physics, etc., are more easily and more naturally represented by polar equations than by rectangular equations. So as an example, you'll see that graphing a circle in using a polar equation is much easier than graphing a circle using rectangular equations. So we'll do a quick review of polar coordinates, polar equations, and then we'll get to talking about graphing a few different kinds of polar equations. So remember the definition of polar coordinates. I'm not going to go through this entirely because we've already looked at it a couple times, but just remember that we have the polar coordinate pair, r theta, where you trace out theta and then you move out the length of r depending on the sign SIGN of r. And then the relationship between polar and rectangular. This is going to be an important piece, especially if we have a case where we're converting. But just remember that x equals r cosine theta and y equals r sine theta. And we use Pythagorean's theorem and tangent to find r and theta to go from rectangular to polar. Now, as we've talked about before, a rectangular grid is helpful for plotting points in rectangular coordinates. So to plot points in polar coordinates, we need to use a grid that consists of circles centered at the pole and then rays emanating from that pole. So if we look over here at our polar grid, we have our origin here, we have our polar axis, and then we have angles all the way around. This should feel like the unit circle, right? Like if we start at 0, we rotate counterclockwise around some number of radians if we're positive, or clockwise if we're negative. And then of course, each of these, that would be like 1 unit, 2 units, 3 units, 4 units, etc. So that's what a polar grid looks like. We'll use this to graph a polar equation. So let's graph r equals 3. So thinking about this, what does it mean for the radius to equal 3? So if we're saying that our function is r equals f of theta, which equals 3, then any angle theta that we give to the function f, we just get 3 out. So, we can create a t-chart. So if we have theta and f of theta, what do we get if we plug in 0? What do we get when we plug in pi over 4? 3. What do we get when we plug in pi over 2? 3. What do we get when we plug in pi? 3. So you're maybe starting to get the sense of what this would look like. If we plot these points, we go out 1, 2, 3 units. 1, 2, 3 units at pi over 4. Again, we're tracing out theta first and then moving out that distance. So now we go over to pi over 2, and then we trace out 1, 2, 3 units. Go to pi, trace out 1, 2, 3 units. And indeed, the graph of r equals 3 is a circle. Much, much nicer than the equation x squared plus y squared equals 9. Right? That's what the equation for a circle would be if we were in rectangular coordinates. We can write it simply as r equals 3. So put that in the back of your head. Now you can identify that this would be a circle if you ever see something that looks like r equals 3. Let's do another one. So what does theta equal pi over 3 look like? So this is kind of like, if we think about x equals, 3 and y equals 2, x equals 3 is just a vertical line and y equals 2 is just a horizontal line. So maybe it would be true that theta equals pi over 3 would also look like a line. So this one, I don't even know if we need to do a t-chart. Essentially, we're just saying that all of the points are pi over 3 satisfy this equation, theta equals pi over 3. Every angle that we're working with is pi over 3. So if we trace out to pi over 3 here, could we give it r equals 1? Sure. 2? Why not? 3? Of course. What about negative 1, 2, and 3? Yeah, no problem. So what this looks like is a line. And if we wanted to convert this to rectangular just to see maybe what the slope is of this line, we could say, okay, y over x equals tangent theta, where theta is pi over 3, and tangent pi over 3 equals, what's that, root 3? So we have y over x equals the square root of 3, therefore y equals root 3x. So the rectangular equation of the line theta equals pi over 3 is a line with slope root 3. Let's do one more. We'll sketch a graph of r equals 2 sine theta. Now this one will be a little bit different maybe. This feels like a solid step forward from considering r equals something, theta equals something. Now we're going to actually see what the relationship between the two is. So again, I think this is useful to do a t-chart. So if we plug in 0, what do we get out? We get 2 times sine of 0, which is 0. So 2 times 0 is 0. What about if we plug in pi over 6? Pi over 6 plugged into f, we have 2 times sine of pi over 6. Sine of pi over 6 is a half. So 2 times a half is 1. How about pi over 4? Pi over 4, that's root 2 over 2. So 2 times root 2 over 2 would be root 2. Pi over 3. 2 times sine of pi over 3 is 2 times root 3 over 2. So we have root 3. Pi over 2. We have sine of pi over 2 is 1, so we get 2. All right, so let's plot these points, and maybe we can see what's happening. So at theta equals 0, we have 0. At pi over 6, we have 1. At pi over 4, we have root 2. Now remember, the square root of 2 is roughly 1.4. So that's like here. Then at pi over 3, we have the square root of 3, which is roughly 1.7. And pi over 2, we have 2. So you could complete this, go all the way around. So we've done a quarter of a rotation around the unit circle, quote, quote. So if you keep going, you'll find that we end up with something like this. And that looks like a circle. A circle kind of above the polar axis. Now, interestingly, if you were to complete the rotation, we would get the same numbers, right? We would just kind of trace over itself. And just for the sake of doing it, like what would we get if we were at 5 pi over 4? So sine of 5 pi over 4 would be negative root 2 over 2. So sine of 5 pi over 4 would be negative root 2 over 2. 2 times negative root 2 over 2 would be negative root 2. Now, if we're at 5 pi over 4, we trace all the way around. If we trace all the way around to 5 pi over 4, and then go negative root 2, look where we end up. We just end up back on the circle. So it actually traces over itself twice in the domain 0 to 2 pi, which that should feel a lot like sine, right? Sine kind of takes on the same values twice in the domain 0 to 2 pi. So if we were to graph just r equals sine theta, that would just be a circle too. So some common polar curves. Circles and spirals. If we have the equation r equals some number a, we have a circle kind of around the origin. If we have r equals a sine theta, we just have a circle above the polar axis. If we have r equals a cosine theta, we have a circle rooted in the origin, kind of on the right, around the polar axis. And if we have r equals a theta, we have a spiral. This one we didn't talk about, but you kind of get the sense of it by thinking through it in your head. If we start at the origin, and the radius, r, is growing at the same rate as theta is growing. So if we start at the origin and we start rotating around, then we just have, essentially, a number multiple of the angle. So it's just growing and growing. So it'll spiral out. And then theta equals a, we just have a line. In the next video, we'll look at some more complex polar equation graphs.